I can cook up some really nasty functions, give them to you, and then ask you to differentiate them. For instance, I could ask you to differentiate this function, 1 plus x squared to the 5th power, 1 plus x cubed to the 8th power, all divided by 1 plus x to the 4th, this to the 7th power. In principle, there's nothing stopping you from just plowing ahead and computing the derivative. You can totally differentiate this function. Right? What's the derivative of this function? Well, this function's a quotient, so you can use the quotient rule. The denominator of the quotient rule is the original denominator squared, so it's going to be the original denominator now to the 14th power. In the quotient rule, the numerator starts off with the derivative of the original numerator. Now the original numerator is a product, so I'll be able to do this derivative by using the product rule and chain rule. So it's the derivative of the numerator times the denominator. And then it keeps going, right? Then I got to subtract the derivative of the denominator times the numerator. But look, you can do this derivative just by a careful application of the quotient rule, the product rule, the power rule, and the chain rule. There is one thing stopping you, your sense of human decency. It's just an awful calculation. Nobody would want to do that. So instead, I propose a trick. But maybe it's not a trick, because it's a trick that fits into a general theme. It's logarithms. Logarithms turn exponentiation into multiplication and multiplication into addition. Let's see how this helps us. So here we go. Instead of calling this function f of x, I'm just going to call it y, because I'm getting ready to do a sort of implicit differentiation. I'm going to first apply log to both sides of this, and I'll get log y. And what's log of the other side? Well, it's log of a quotient, which is a difference of logs, and logs of things to powers, which is that power times log of the base. So this works out to 5 times log of 1 plus x squared plus, this log turns multiplication into addition, 8 times log of 1 plus x cubed, and this quotient becomes a difference, so minus 7, the 7 in the exponent, log 1 plus x. Now we differentiate. All right, so differentiating now, what's the derivative of log y? Remember, y is secretly a function of x. So when I differentiate log y, it's the derivative of the outside, which is 1 over y, times the derivative of the inside, which I'll write dy dx. This is really an example, if you like, of implicit differentiation. All right, now I differentiate the other side. 5, well, that's multiplied by 5. The derivative of log is 1 over, so 1 over at the inside function, 1 plus x squared, times the derivative of the inside function, which is 2x. The derivative of 1 plus x squared is 2x. All right, plus 8, and its derivative of log is 1 over at the inside function, 1 plus x cubed, times the derivative of this inside function, which is 3 times x squared, minus 7 over, derivative of log is 1 over at the inside function, 1 plus x to the 4th, and the derivative of 1 plus x to the 4th is 4x cubed. We're almost there. So now I just multiply both sides by y, and I get that the derivative is this thing we calculated times y. Y is this quantity. I can write this a little bit more nicely. Right? Here's this. 5 times 2x is 10x, 8 times 3 is 24, 7 times 4 is 28, and then I multiplied by y. So I found the derivative. Here it is. In general, this trick of logarithmic differentiation, as it's called, works fantastically well for functions like these, rational functions that involve a lot of high powers.